Now we're going to talk about tissue perfusion and then the fluid balance in tissues. So for tissue perfusion, I want to highlight two things. And I will try to put it in writing, okay? So this is what I want to tell you. So, tissue perfusion is secondary to blood pressure. Let me explain what I mean by that. So, from the standpoint of the homeostatic regulation of the body, put the pencils down, seriously. From the standpoint of homeostatic regulation of the body, blood pressure is more important than tissue perfusion. If blood pressure, systemic blood pressure is normal, then yes, your organism will change the blood flow to different tissues as needed. Does that make sense? If you're losing blood and your blood pressure goes down, then sorry skin, sorry urinary bladder, sorry small intestine, we're not going to give you a lot of blood because we need blood for other organs. It's a zero-sum game. Does that make sense? So when we talk about blood pressure regulation, we basically say, look, at this point, organs can go. When we talk about tissue perfusion, we presume, all right, in this particular situation, we think that blood pressure is fine. It's normal, it's as it's supposed to be, 120/70. That makes sense? Little note, which I forgot, put it in writing. Did I talk about pulse pressure? Kind of a side, probably I didn't. Side note, know what the pulse pressure is? I'm going to put it here in the corner. So pulse pressure, systolic pressure minus diastolic pressure. Okay, that's the pulse pressure. That's the definition. Okay. Okay. So like in case of 120/70, the pulse pressure is 50. Okay, does that make sense? Clear?
Like, what is this significant? Like, why do we need to?
We just call it, it's just one of the parameters. We can, it is used to calculate mean arterial pressure. And mean arterial pressure, because every time saying, 120/70, 120/70, you can pretty accurately express it this way. You take diastolic pressure plus 1/3 of the pulse pressure. Okay, so for 120, listen, for 120/70, what's going to be mean arterial pressure? 70 plus 1/3 of the difference, which is 50. So something like 86, 87. Okay, does that make sense? And once you get this one number, it's much easier to work with. Okay, that's it. It's basically it. Good? Got it out of the way. Now, tissue perfusion. What are three main factors that increase tissue perfusion? Generally speaking, is increased when CO2 is high, pH is low, or oxygen is low. Okay? Which kind of plays into this narrative. Look at this. When carbon dioxide is high, pH is low, and oxygen is low, what does that mean? That means that tissue is metabolically active. Does that make sense? Is that clear? Tissue is metabolically active, that will increase tissue perfusion. Okay, good? Now, so this is called metabolic mechanism of regulation. Okay? And remember, so tissue perfusion is to comply with the needs of tissue, and it has to be maintained more or less constant. So another mechanism is called myogenic mechanism. And this is how it works. Look at this. When blood pressure, systemic blood pressure, in the short term increases, what happens now, think it through, what happens to the diameter, local diameter of the local blood vessels? When pressure of the blood in the blood vessel, look at my hands, pressure of the blood in the blood vessels increases, what happens to the diameter first? Imagine you have like a very elastic pipe and you open the faucet. What's going to happen to that pipe? It's going to expand. Does that make sense? Just simply because the blood pressure for a very short term goes up. This is the short-term regulation. So blood pressure goes up, blood vessels stretch. Does that make sense? To compensate for that stretch, now they're going to constrict. Basically, what you did, Emma, you basically skipped a step. So yeah. Okay? Does that make sense? So increased blood pressure will result in the stretch of the local blood vessels, which will result in vasoconstriction to maintain the same level of perfusion. Now, let me ask you this. What if there's a short-term decrease in blood pressure? What's going to happen? Local blood vessels are going to shrink first. This will result in vasodilation, right? Which will still maintain perfusion constant. Clear? Now, why we talk about these two mechanisms? Because different tissues use different mechanisms in different conditions. Does it make sense to you? Okay? Now let me support my words with some examples. So we're going to talk in details about two tissues, and I'm going to briefly touch on the cardiac tissue as well. Let's talk about what, in my opinion, the most interesting one is the brain. Okay? So let's take a look at the regulation of blood flow through the brain. So in the range of the normal blood pressures, and by normal it's a pretty wide range. So we're talking about mean arterial pressure, MAP, being between 50 and 150 millimeters of mercury. You don't have to memorize these numbers. But the point is, normally the mechanism of regulation is myogenic. In the notes, I have this little illustration of the diameter of the brain blood vessels as blood pressure continuously rises. So look what happens. So look, this is the blood vessel in the brain at say 60, mean arterial pressure 60, okay? When it goes up to 70, when it increases, what happens to the local blood vessels? Initially stretch, and in response to that, they will constrict, right? And as the pressure goes up, like if you look at the graph, blood vessels are going to be narrower and narrower to maintain the same level of perfusion. Because, you know, elevated blood pressure means blood flows much faster. So you don't need to have like that massive of a vessel. That will suffice. Is that clear? Now, what happens outside of this range? When blood pressure goes way above the like 150 mean arterial pressure, this mechanism doesn't work anymore. And here's what's going to happen. So go from this mean arterial pressure continues to rise. Blood vessels start to dilate. It's not even dilation. They basically are giving in to the pressure. Does that make sense to you? They give in to the pressure. So tissue perfusion, brain perfusion starts to grow astronomically. And when you have too much blood coming through the blood vessels, it inevitably leads to edema. Does that make sense? So basically what I'm trying to tell you that in people with uncontrolled enormous hypertension, they may end up with a brain edema because, you know, really high blood pressure, blood vessels are stretched, they will become leaky, inevitably. Does that make sense? And the opposite, look, the opposite, here's what happens. Imagine that your blood pressure goes down. It goes down, blood vessels dilate in the brain. Okay, dilate, 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 and at some point, they lose the ability to respond via myogenic mechanism, and as blood pressure will decline below those 50 millimeters of mercury in arterial pressure, they will start collapse, collapse, collapse. Tissue perfusion will go down and down and down, and first you're going to pass out. Okay? Does that make sense? Now, is there a role for metabolic mechanism? Of course. But metabolic mechanism, as you can see, is engaged when CO2 goes up. Now let's take a look. So we just established that for proper function of the brain is really important, right? And it's pretty gentle. So for proper function of the brain, we want perfusion to remain the same, to remain standard. Does that make sense? Let's say, for example, for some reason, due to, I don't know, some weird event, brain CO2 rises, and rises a lot. Okay? Look what happens. Increased CO2 results in the increased perfusion, which basically means suddenly you have a rush of blood into the cerebral vasculature. Does that make sense? You've got this rush of blood in the cerebral vasculature that may result in the brain edema. I'm gonna put a question mark because it's not always, right? But it can be. Now, here's the thing. It all sounds very sort of generic. But imagine that you decide to go up in the mountains. And I'm talking like Mount Denali, right? Some really hot, like, well, Colorado probably won't cut it. It's still pretty low, but say Mount Denali. So climb up there, oxygen levels in the air precipitously drop, right? So your brain suddenly gets overwhelmed with elevated levels of CO2, okay, which increases brain perfusion. And this is one of the problems if people do not do proper accommodation as they climb the mountain, ascend the mountain. They will end up with brain edema and they can die, like easily die from that. That makes sense? Now, another tissue that I wanted to mention is muscle. Muscle is pretty simple. increased activity. Basically, muscle perfusion is almost entirely through the myogenic mechanism. Okay? Increased muscle activity results in the increased production of CO2 and acidification, which results in the increased perfusion. Muscle blood vessels can do it easily. Okay? Does that make sense? Now, cardiac is mostly metabolic as well, but it is largely stimulated by decreased pH. Okay, I'm not going to put it in, we're just mostly metabolic. So muscle tissues are mostly through metabolic, brain is mostly through myogenic in a normal situation. Okay, we're good?